Good morning. So, as you can see, we're going to look at hypothesis testing today. This is for my Bio 175 class, which is biostatistics. And for a little bit of background, this is our first session back during the COVID-19 social distancing quarantine times. So, the modality at which we're going over the course material is jarringly different right now. Also, on the teaching side of things, for most of the students in this class, this is the third or fourth statistics class that they have taken. So, my intention here today is to simply refresh our skills a bit. And I'm challenging myself to give kind of a refreshing lecture on the material as well that is not completely redundant with what the students have already seen before. So with that, admittedly, I'm going to do the coding live in kind of an improvisational way. That is, I haven't completely planned things out in advance. So let's just see how the hour goes. Alright, so as you can see on the screen right now, my plans for today are to refresh our memories of how to set up null and alternative hypotheses. We'll refresh our skills with two means hypothesis testing, which is the so-called t-test. And while we're here, especially because I've assigned homework to these students about 175, we'll look at more advanced ways to customize the x and y axes on plots. Now, like what we did with testing for normality was the Shapiro-Wilk test, which we saw was an example of hypothesis testing. What we'll do is create some artificial data where we already know what the means and medians are to see how the calculations play out with hypothesis tests. So what I'm going to do is I'm going to generate some artificial data right now, and I'm going to use the normal distribution. And as you can see from the side note I just typed, the mean and median are the same for the normal distribution. We'll let capital N be some relatively large number. Let's just say 50 for now. And as you can see, what I've done is I made two sets of data from normal distributions. Both of them have mean 18, but they have two different variances for the moment, just so that we have something to see in the graph in just a bit. And I'm going to assign some really quick categories names 1 and 2. That is, we have group 1 with 50 observations, and group 2 with 50 observations. As usual, I'd like to visualize what's going on, so we'll run into a ggplot. But because we're going to use ggplot, we'll load the packages. Because we're using a ggplot, we'll make a data frame. And like usual, we'll pipe that data frame into the ggplot. What we'll look at today are box plots, because what I want to focus on is where the medians are. So the idea is between a couple different categories or a couple different classifications within a category called data, a variable, we're going to compare the means between them, which are happen to be represented by the thick black line in the middle of the box plots at the moment. So let me go ahead and label the graph while we're here. So we're going to compare these two sets of data in the sense of we're going to try to describe if the data are in some sense the same or different. So our null hypothesis are that the means between the two sets of data of random data from the normal distributions are the same. And the alternative hypothesis would be that the means are different. Now, the way we presented this skill in past statistics courses is to run through the t-test function in R. What I'm hoping to do today and here in this month, we're entering April 2020 at the moment, is to lead us right into more complicated situations. So we're doing hypothesis testing where there are more than two groups or two classifications, and also to pave our way right into ANOVA as well. So what I want to do is also be able to pipe the t-test right into our tidyverse or deploy our way of thinking. But first, actually, we should do a t-test normally. So we're going to compare the observations by category. Because of the way I'm arranging the information going into this t-test function, we have to indicate where the data is coming from. The syntax here is that we're putting our dependent variable, or what's on the vertical or y-axis, first, followed by the tilde key, and then our independent variables, or what's on the horizontal x-axis, after the tilde. In data science parlance, this is what we're trying to predict on the y-axis, and then the predictor variables on the x-axis. In short, y tilde x. So recall that by default, R does what's called a Welch two-sample t-test. We have a sample statistic coming from the t-distribution. The degrees of freedom largely based on how much data were there in the first place. We'll come back and focus on the p-value in just a bit. By default, R gives a 95% confidence interval for how different the means are. And in the random data I ran so far, Group 1 had a mean of about 18 units, and Group 2 had a mean of about 16.6 units. So the question is, are these means different enough that we could claim that they're different enough with some sort of statistical significance or not? And as you recall, what we tend to do in practice when we want to be frank, is to grossly summarize all this by focusing on the p-value. I'm going to run this plot again. And my intention for this earlier example is that the means are really close together. The means being the thick black line in the middle of the rectangles. So when that happens, we could focus on the p-value here. By running the t-test and attaching this $p dot value. So rather than printing out all the results from the t-test, we could focus on the p-value here. Recall that scientists usually like to compare the p-values to 0.05 for that level of significance. So we say that since this p-value is greater than 0.05, we fail to reject the null hypothesis. The null hypothesis was back up here, saying that the means are the same. But because our p-value is greater than 0.05, we, in some sense, do not have enough evidence to claim that these means are different. And in careful language, we say that we fail to reject the null hypothesis. And then likewise, if we have a p-value less than 0.05, the jargon is that we reject the null hypothesis. I'll take a pause here to take a breather and welcome any questions from the folks in chat. Okay, so now what I want to do is run through this code again, but with a slight, well, not slight, actually, adjustment to some of the false data that I've created. So I'm going to grab that code above. But this time around, I'm going to change the means here. So I'll change the mean, the average of the second set of artificial data to 175. So that way in our box plots, we get a case where the data are clearly separated from each other. The null and hypothesis tests are the same. We're asking if the means are the same, and we'll see how this plays out. And what we'll be doing, especially as we're dealing with more and more complex data, is going into our dplyr skills, namely the pipe. So what I'm going to do is, with the summarize command, extract the p-value from the t-test. So here, since our p-value is admittedly in this artificial setting, since our p-value is so very small, definitely less than 0.05, we will reject the claim that the means were the same, which makes sense because I had intentionally made a situation where the means were quite different. So while I'm here, what I thought we'd do is also go over a relatively new skill, and that's to customize not only the label on the X and Y axes, but also where the numbers are. Where the numbers are called the tick marks. So what we're going to do is also adjust where the tick marks are. Now we call for box plots along the y-axis. Let me actually type this all out. Along the x-axis, we have our categorical variable. And this will play out in the commands we're going to look at right now are called discrete in this quest to relabel some things. And along the y-axis, we have our numerical variable. So that will be called continuous when we do some labeling here. Let me, for the sake of trying to make a good tutorial, let me make a separate code block for this idea. So what we're doing right now is we're relabeling the tick marks. And I'll fully admit, I don't have all this completely memorized. So whenever I try this skill out, I search the web. I do a Google search for ggplot x change like x-axis tick marks or whatnot. So let's see. Along the x-axis, we have our categorical variable. We'll use this command here, scale x discrete. And first, this is one way we could relabel the x-axis. So you could see that I've now put the words R groups down here on the x-axis. Next, I'm going to see if I could change the numbers 1 and 2. Actually, let's use some medical testing paradigms. We have a control group and a test group. And that will change our labels there on the x-axis. Now for the numbers on the y-axis, that was our continuous variable. So the command we're going to try out today is called scale y continuous. With the name parameter, we could once again change the label on the axis itself. I'll just call this level for now. Now, let's see how this plays out. So say if for some reason I really only wanted to highlight these two numbers, 18 and 175, I will explicitly label those particular numbers with the breaks command here, with the breaks parameter. Now, because I only put in those two values for the y values, the graph was kind of shrunk a bit, kind of rescaled. So what we could also do is bring back how far the y-axis will go with the limits parameter. And that will stretch the graph back out a bit in the vertical direction. In summary, when you program in R, especially in ggplot, we could use commands like this, scale discrete and scale continuous, to have a lot more control over what we have on the x or y axis. I'll take a pause here to see if any of my students have a question. So we'll go over a more of a real world example here. Each semester for the students in my various classes, I have them fill out what I call the demographic survey. It's to collect a lot of data. The survey itself has about 130 questions, and the purpose of this is to gather data about the students themselves. So when we go over examples in class, the examples will be about them. This semester, I had about 400 students. The data is a CSV file. So I'll go ahead and load that in. That is, because the data is a CSV file, we're going to use the read CSV function from the readr package. running into quite a warning there. Let me double check something. That's not quite what I wanted. So the column names at the moment are not attached to the data. So I have the variable names saved in a separate file. And the point of this was to have easy to type variable names so that we could dive into our data. One of the questions I asked the students was how many units have been completed before this semester? And we could quickly get a sense of that result with the summary command. Unfortunately, when some of the students filled out this survey, they just felt like putting in very false numbers. So we could see an outlier that someone claimed that they took 4,444 units and you need 120 to graduate. So we should somehow get rid of the outliers here. So what I'm going to do is let's say 130. For students that claim that they have already completed more than 130 units, I'm going to wipe out that data. Put in NA for missing value. So now when we see our units completed variable, they have a median of 76 units completed. Uh, for my students, this is across Bio 18, Bio 175, and Math 32. And our maximum right now is at 130 just because that happens to be where I had to cut off. And there are 38 missing values. the warning that will appear here when I make the box plot is to also indicate that there are 38 missing values. And here we have a quick box plot of what's going on. Have the good habit of labeling the graph. We'll worry about the x-axis in the next example, but for now, let's change the units on the y-axis with our new skill. So I'll fix the label on the y-axis to something a little cleaner, easier to read. And the way the unit system works at our semester system school is that the division between first year, second year, third year, and fourth year students tend to be at 30 units each. So I'll change the breaks so that we have those labels now along the y-axis. And I'll give the graph, in some sense, some room to breathe by expanding the limits as well. The main skill today was, of course, comparing two different groups for their means. So what I'm going to do, and again, I'm just kind of doing this improv. I did not completely plan this out in advance. So we'll create a new variable called going to graduate. My intention here is to divide the students into the classifications whether or not they're a senior or not a senior. So let's see here. Let me bring up the variable names again. And I called that class standing for freshman, sophomore, junior, senior. And I'm going to save that right back into our DF, into our data frame. So what that does is it creates this new variable with this classification. And you could see in my data that amongst my students this semester, 127 of them labeled themselves as a senior, and I grouped the rest of them together in this category called not a senior for the remaining 267 students. So now with the ggplot, with the box plot, I'm going to put going to graduate on the x-axis. And you can see now we have the two different box plots, and that's what we're going to compare. We have some missing data. Some students skipped this question. And there's also some students that indicated that they were a senior, but strangely enough, indicated that they had completed a low number of units, and that might be bothersome in the data, but we'll not address that part today. One way I like to get around the missing data is to, if I know I'm only going to use these variables in my graph, I'm going to put those variables in this select function here. Be sure to have the pipes at the end. And what this line of code here does is filter complete cases will only report and graph the students that did fill out that units completed and the class standing variables. So now the graph will avoid the missing data, and we can focus on these two box plots here. Now, as far as the hypothesis testing is concerned, you can probably see where I'm going with this. I anticipate a situation where we're going to claim that seniors and other students took the same amount of units, and then see how that claim runs. So our null hypothesis, for the mathematical underpinnings, we always use the equal signs or equality. So as you can see there, my null hypothesis is that seniors and other students took the same number of classes or same number of units. Whereas the interesting hypothesis, or the one that's more colloquial, would be in the alternative hypothesis, saying that seniors took more units than other students. So we'll put units completed on the y-axis, going to graduate on the x-axis. We're going to specify that our alternative hypothesis was greater. And we're going to focus on the p-value. Now I gotta worry about the order of how these categories played out. So you notice in the graph, the students that were not a senior appeared first and senior appeared second, simply in alphabetical order. That's why this p-value was strange. I actually have to flip this around. And now we got our p-value. That is to say, the alternative hypothesis is that not a senior were less than, had fewer units than seniors. Now we have a p-value that's less than 0.05. And to state that fairly clearly, since the p-value is less than 0.05, we reject the null hypothesis that seniors and other students took the same number of units. And hopefully that all makes sense. I think while I'm here, we'll do one more example. Something I've always been curious about is at our university, do GPAs tend to change either for better or for worse in the last year? How do seniors tend to have their GPAs? So let me refresh my memory of the code we encountered so far. So here we could see a quick summary of the GPA, what the student self-reported. Now, our university is on a 4-point system, with 4 equaling A, so a GPA of 5.0 does not make sense in our system. We'll go ahead and remove the outliers. And what I'm doing here is for students that reported a grade point average being 0 or greater than 4, I'm going to erase those and put in NA for missing value. So now our grade point average results are a lot more realistic. We see a median GPA of 3.0 and a mean of around 3.0 as well. This has not been stratified, so this is amongst students of various majors and different paths in the university. I'm going to grab the box plot code I did before. But the changes is that instead of talking about the number of units they completed, the students completed, I'm going to change this to GPA. have to change what's on the y-axis. So we have our comparison between the students that are seniors and not a senior. Now, I just realized the time frame. When I asked students simultaneously what the class standing is, and they said that they were a senior, and then when I asked them when they were GPA, their GPA still reflects their courses that they took before senior year. Now, because the labels on the x-axis are fairly easy to understand in context, I'm going to erase this going to graduate label. And one way to do that is simply say along the x-axis, put in nothing for the label. So now we have that done. And at least according to the medians, the median being the middle of the box plots, it appears that the median GPA for seniors is lower than for the younger students. And we'll see if there is a statistical significance. Our null hypothesis has to be phrased this way, that seniors and other students had the same GPA. And we'll do what's called a two-sided hypothesis test by saying that the alternative is simply seniors and other had a different GPA than other students. One more time, we'll focus on the p-value. The p-value, whoops, I should have left that up there. The p-value is less than 0.05. I honestly did not know that in advance. So we reject the claim, we reject the null hypothesis that seniors had the same GPA as other students. And thus, from start to finish, again, today I hope it was a good refresher of how to carry out hypothesis testing. I've also shown how we could take a categorical variable such as the class standing, freshman, sophomore, junior, senior, split that up into two different groups to make it easier to set up a hypothesis test. We also customize the x and y axis to have greater control over the labels and tick marks. At least in my opinion, I think that was a pretty productive day. I'm gonna end the session here. This video will be uploaded to YouTube, and otherwise, let me just say, have a nice day. Bye.